All right, let's look at how we set up the problem using the simplex method. We need to set up a matrix. So I provided all these notes for you. You can read them after. And the problem that we're going to use today to set one of these up is a maximization problem. As we move forward, we're going to have one section donated to solving only maximum problems. Maximize this subject to these constraints. Maximize this objective function subject to these constraints. With usually our problems are going to be such moving forward, because all of our applications involve positive numbers, we'll have x greater than or equal to 0 and y greater than or equal to 0. So we're working in the first quadrant. So that's what this one means here. If we happen to have more variables, then, but usually it's just going to be x greater than or equal to 0 and y greater than or equal to 0. But because we, might run out of the alphabet here, what we generally do instead of having x greater than or equal to 0 and y greater than or equal to 0, we're going to use subscripts. And so we're going to have x1 greater than or equal to 0, x2 greater than or equal to 0. If there are more variables in the problem, then x3, and then x4, and x5. And the simplex method will allow for more than just 2 variables. So that's what this means here. These are the non-negative constraints, they call them. You're going to have an objective function, and generally we're going to call it P. And I think the reason we use P is because in many of our applications where this linear programming is used in the real world, the job is to maximize profit. So the P stands for profit. And this just says you have some number times x1 plus some number times x2 plus some number times x3 and so on. In our previous problem, it looks a lot like this, but we'll be using P instead of Z. So it's going to be a linear constraint function. So 4 times x1, negative 2 times x2, and so on. And then we're going to have constraints. And the constraints are the inequalities. Sometimes you'll have one, sometimes you'll have many. But what's key here is that in the maximum problem, you must see less than or equal to a positive number. And that's what they're saying here, B is positive. Less than or equal to a positive number. So you need the standard form to be intact, and that's what they're talking about in here. Next, the thing that you need to understand in this process is this idea of a slack variable. So notice all of the constraints are going to be less than or equal to some positive number, less than or equal to some positive number. So this one here, if x1 plus 2x2 is less than or equal to 32, then there's this number out here, we'll call it S1. This is what S1, S2, S3, these are the slack variables. And these slack variables are going to also be non-negative. So if x1 plus 2x2 is less than 32, then x1 plus 2x2 plus some unknown amount will make it equal to 32. So where x1 plus 2x2 is lacking, we add something to that, and that picks up the slack and makes it equal to. So what we're going to do here is we're going to write inequalities as equations, and then we're going to solve the systems of equations. In the next one, we have 3x1 plus 4x2 is less than or equal to 84. So if we add something to the 3x1 plus 4x2, we could make it equal to 84. And we don't want to use the same slack variable, so we'll give the next one a different subscript. And again, slack variables will be non-negative. So part of the problem, setting it up, will involve writing these slack equations. They call this format here the I system. This is our author's notation because it includes inequalities. So the I means the inequality part, representation. So this is the I system. And when we convert it to the slack variables here, this is called the E system. I system and E system. E electronic, I guess we're going to feed this matrix to a program. So you'll see things like convert this I system to this E system and so on. Or if this is the E system, what must have been the I system? Now we're going to solve a linear programming problem. And it's going to be very similar to identifying those corner points, but it turns out that the corner points will appear in this process here when we look at systems of equations. And we're going to solve many, many, many systems of equations to find all the possible corner points, or all the possible places where these slack equations intersect with one another. So here are the steps. The first thing we're going to do is we're going to use slack variables to write the I system as an E system. That is, to convert the inequality system to that it contains less thans and greater thans, and less than or equal to, greater than or equal to, and we're going to convert those to equations. And then basically it says form a table of this size with this many rows and this many columns, and start assigning zeros to any combination of either the decision variables, the x's, or the slack variables. And I'll show you how to do that. It says continue until all the rows contain all possible combinations of assigning 2 zeros to the variables. And of course, this is a 2x2 system they're talking about. All right, complete each row to find the solution to the E system. And I'll show you how to do that. You can use Gauss-Jordan if it's harder, but a lot of times you can just do these in your head. And the second part of the fundamental theorem of linear programming basically says that the solution to the bounded maximum linear programming problem will occur at one of those corner points, but we don't call them corner points in the table method. I'll point out some of these things once we get to the problem. But if our original system just has x's and y's to it, if we have 3 inequalities, we're going to have 3 slack variables. So really the solution would be an ordered quintuple here, instead of just an ordered pair, where 2 of these numbers will be zeros. The ones that are zeros are called the basic variables, and the ones that are not zero are called the non-basic variables. Again, I'll point to some of these definitions as we work through a problem. All right, so I just provided you all the notes, and I don't know that all of this is necessary. All right, let's start with from the beginning. And what they have here is a system of equations. This is called the E system, because it's got the equations. E for equations, I guess that's what it means, and I for inequality. Now, since you know this came from a maximum problem, the maximum problem was probably this. You had 2x1 plus 5x2, and then the inequality sign is in a maximum problem is always less than or equal to 10. Now what we're going to do is we're going to write down all of the different variables here. Later on, we're going to add one more column, and that one more column is going to be the value of the objective function. So I'm going to give a column heading to each of the variables that I see in my 2 equations here. I see an x1 and an x2, and those appear in both of these equations. And then I see an s1 and then an s2, but they only appear in one place. So what they're saying here is that, and I'm just going to go in a row here, because this 10 through 12 here, what they've done is they've actually given you most, if not all, of the way you set up this table. So for example, in this one, x1 is 0 and s1 is 0. That's what they're telling you. So when you solve the system, then you have to figure out what the value of x2 and s2 are. And here's how you do it. You start with the original slack equations like this, and we were given that x1 is 0 and s1 is equal to 0. So what we're going to do is we're going to plug zeros in for both of those variables. Let's see what happens when we do that. x1 is 0 and s1 is 0, like that. If we let those 2 variables be zeros, then this equation, after we simplify, will be 5x2 equals 10, and then you can solve this by dividing both sides by 5. So the value of x2 then would be 2. So we'll put a 2 here. This other equation here, we have 3x2 plus s2 equals 8 after we replace the x1 with its value here, 0. we get this. And then we just found x2 to be 2. So we're going to put 2 in there for x2. And that's going to give us 3 times 2 plus s2 equals 8. 6 plus s2 equals 8. Subtract 6 from both sides, or s2 equals 2. So that's the work for each one of these problems. S2 is equal to 2. So there it is. Now creating the whole table is kind of doing problems 9 through 12, all of them. So in this one here, x1 is going to be 0, and now s2 is 0. And then you need to go find x2 and s1. In number 11, you have x2 is equal to 0, and s2 is equal to 0. And then in number 12, you have x2 is equal to 0, and s1 is equal to 0. So the problems are similar. Why don't you go ahead and put the answer in the chat to number 10. That is, say x2 equals and s1 equals. If you don't know how to do this, then just write your name in the chat. I want to make sure you're still here. I think your answers are going to be fractions this time. Just write the simplified fraction form. Okay, looks like you got it. Yeah, I mean, sometimes you're going to have these messy solutions. Remember that you can do this with the calculator, solving systems of equations. So the matrix that you'd have to enter in for this one, remember you have, you're looking for x2 and you're looking for s1. And then you've got the right-hand side. So the x2 coefficient here is 5. The s1 coefficient is 1. And the right-hand side is 10. In this one, the x2 coefficient is 3. There is no s1 in here, so 0, and then 8. So this would be your original matrix. Do RREF, and then you would see 0, 1, or 1, 0, 0, 1, and then here you'd have the 8/3, and here you'd have the negative 10/3. And so this is the value of x2, and this is the value of, all right. So you have to do this numerous times in any one given problem. And so you can see that we still have a couple to go here in order to get the entire table. All right, so keep in mind that we will be doing this on every problem from start to finish. And at some point, we're going to ask the calculator to do it for us. Okay, write the E system obtained via slack variables for the given linear programming problems. All right, I might as well, so here we have 1 and 2. We have 2, we call them constraints, not the basic constraints, not the x1 greater than or equal to 0. We don't count those. But for the non-basic constraint like these two, there are 2 of them. That means that we're going to have 2 slack variables used in this process. So, and I'm even going to write the, all they want is the slack variables. It says write the E system. Okay, let's write it. All right, so P, and then I'm going to bring the 5x1 over to the left-hand side along with the P and bring over the 7x2. Yeah, in this equation, there are no slack variables, so maybe I'll just say 0s1 and 0s2, and then equals 0. So basically, I manipulated this equation by subtracting 5x1 from both sides and subtracting 7x2 from both sides, and that left a 0 on the right-hand side. All right, for this next constraint, we have 2x1. By the way, notice it's less than or equal to a positive number, less than or equal to a positive number. And you have the basic constraints here, non-negative constraints, they call them. All right, so 2x1, and then I'm going to try to line up all the variables. So all x2s will go here, all x1s will go here. Now, if 2x1 plus 3x2 is less than 9, then we can add a slack variable that will bring it up equal to 9, where s1 is greater than or equal to 0. So that's how you would transform the first constraint to an E constraint, equality constraint, instead of an inequality. The next one, we have 6x1 plus 7x2, and we add those two together, we get something that's less than 13. So if we add another slack variable, will bring us up equal to 13 for some s2 greater than or equal to 0. Yeah, that's it. Basically, you're writing the objective function and the two constraints. And it turns out that the objective function and the two constraints, those are going to be what goes into creating our matrix in the simplex method. We're not really going to use the non-negative constraints here in our matrix, but just to know that we have to have all variables to be non-negative. Okay, why don't you try number 16? In this one, since we have 3 non-trivial constraints, they're all less than or equal to some positive number, 1, 2, and 3. Since we have 3 in this one, you're going to introduce 3 slack variables, an S1 and an S2 like before, but since we have a third constraint, you need to introduce a third slack variable. I usually don't write all these zeros, but without the zeros, this is what you would have. You can see in the bottom row here, this is where I put the objective function, and it's the only equation that contains the variable p, this thing that we're trying to maximize. So we have the p variable column, the x1 column, the x2 column, the s1, s2, and s3, and then we're going to call this one over here the right-hand side. I think I've used that notation before, but what you'll see later is that this is exactly, if you just get rid of all the variables and you just use the coefficients only, this becomes the matrix that we enter into the calculator, and it's called the initial simplex table matrix. It's not, well, I guess it's just a fancy matrix where everything is supposed to be in the right spot. Okay, so if you wrote everything that I've written here in black, you'd have it correct. So you should have 4 equations here. All right, so what we're doing is we're going on and we're going to continue to make progress towards this whole process. So let's take a look at another problem. And I think this is related to the other ones, but they want to know, again, just so our terminology and we can talk to one another, is they're defining all these terms. So basic solutions to the E system. So we would have 2 constraints here. Was this just like our other one? No, I think it's different. So here is your E system. And if you wanted the I system, then you'd need to go backwards from what we did, right, in that previous problem. Go from the slack equations back to the inequalities. So 2x1 plus 3x2 is less than or equal to 24, and 4x1 plus 3x2 is less than or equal to 36. Now there's no objective function in this one, but what they've done is they've created a table. Grab something from the first handout here. M plus 1 times m plus 2 over 2. Form a table with this many rows and this many columns. M would be the number of slack variables used. So in this one, we have 2 slack variables. So M is equal to 2 slack variables, right? Then if M is equal to 2, and we plug it in here, we're going to have 2 plus 2 times 2 plus 1 divided by 2. That's 4 times 3, 12, divided by 2 is 6. So we're going to have 6 rows. That's what this means. And we're going to have m plus 2, 4 columns. 6 rows, 4 columns. 6 rows, 1, 2, 3, 4, 5, 6, denoted by A, B, C, D, E, F, and 1, 2, 3, 4 columns. So just think of the data inside. 4 rows, 6 rows, 4 columns. All right, the basic solution. All right, so x1, x2, s1, s2 equals. And so what they want is the basic solution for A. And so what you put in there would be 0, 0, 24, and 36. x1 and x2 are basic. And the definition of the basic variables will be all the variables that equal 0. Okay, when we create these inequalities here, or these slack equations from the inequalities, we're saying that if 4x plus 3x2 is less than 36, then 4x1 plus 3x2 plus some other variable brings us up equal to 36, but that s2 has to be positive. So S1 is positive, non-negative, I guess we say, and S2 is as well. So if we see a solution where X1, X2, S1, if any of those variables are negative, we say that that solution is not feasible. So these two that have these negative numbers in there, these are not feasible because of this condition right here that said that those slack variables must be non-negative, must be positive. All right, so A, B, E, and F are feasible since X1, X2, S1, S2 are all greater than or equal to 0. C and D are not feasible since S1 is equal to -12 or S2 is equal to -12. All right, now we're going to add the final wrinkle here, and that is to add in an objective function. So for number 28, what I'm going to do is I'm going to add a new column to our table and label it P, the thing that we're trying to maximize. So it's going to look like this. And P is equal to, I'm going to grab this from number 28, 8x1 plus 5x2. Notice that in the objective function, there are no slack variables. So we really can ignore the value of S1 and S2 when we're plugging them into the value of P. So in the first one, we have 8 times 0 plus 5 times 0. Well, that's just 0. I'm going to skip the non-feasible ones. In the next one, we have 8 times 0 plus 5 times 8, and that's 40. Ooh, it's getting hard to read. 0, 0, 0, 0, 0, 0, I think. Yep. 0, 0, 0, 0, and then 0, 0. So we're just going to start it like this and just make sure that every possible combination of two zeros are listed there. And then we have 24 and 36, 8 and 12, 12 and -12, 12 and -12, 9 and 6, 6 and 4. And P is equal to 8x1 plus 5x2. All right, I started to get crowded out there. So, all right, so this one, P is equal to 8 times 0 plus 5 times 0, which is 0. So we're only going to be focused on these two columns because P doesn't have any S's in it. We don't have to do C and D because we know that those are not feasible, but we can plug numbers in if we want. All right, so 8, 0 plus 5 times 8, and that one was 40. And these two non-feasible ones, 8 times 0 plus 5 times 12 is equal to 60, but not feasible. 8 times 12 plus 5 times 0 is equal to 96, but again, that's not feasible because we can't have a negative slack variable. 8 times 9 plus 5 times 0 is 72, and then 8 times 6 plus 5 times 4 is equal to 20 and 48. Now, what that theorem here said is that when you do a problem like this and you set up a table like this where you've identified every combination of zeros for two of the variables, that when you look over at these numbers, the largest number that you see that is feasible will be the maximum. So what we're going to conclude here is that the max is equal to 72. It occurs when x is equal to 9, and x1 is equal to 9, and x2 is equal to 0. We don't care what the value of the slack variables are because they're really dummy variables, and we added those ourselves during the process of solving this problem. They're not actually part of the solution, but they're very useful. All right, I'm not going to do it here, but I'll do it in the notes. So if you want to find the system, or if you want to solve the system, if you want to graph this system here, you would have 2x1 plus 3x2 is less than or equal to 24. You have 4x1 plus 3x2 less than or equal to 36. And you have x1 greater than or equal to 0 and x2 greater than or equal to 0. So we know that the solution is going to be in the first quadrant. We could actually solve this linear programming problem using the methods from section 5.3, similar to that problem that you just did at the beginning. And if we solve that and drew the feasible region, you can see that a couple of these points will be outside of our feasible region. All right, so I'll either do it in the notes, or if we have time, I'll come back to it. All right, so many of the homework problems here are just kind of walking you through the steps that you're eventually going to have to walk through to solve these problems. And so let me take a look at one of these. And all right, let's take a look at number 42. If we solve this one graphically, we would have just one inequality, and we'd be in the first quadrant. So you'd have a triangular region that's shaded, a bounded triangular region here. All right, so here is the I system, and they want you to convert it to an E system. We have just one constraint, and so we're going to have one slack variable. And we usually use the S's for the slack variables, and that's going to be equal to 24. And that's it. So our table, write all the variables, x1, x2, and s1. So we want to select two of these variables, two of the three, to be zeros. So we have x1 and x2 is one possibility, x1 and s1 would be another possibility, and then x2 and s2. So we only have 3 rows to this table. All right, I'm going to do this mostly with mental math, right? So if x1 and x2, let's do this, let's find s1 in this first missing one. If x1 and x2 are 0, then 0 plus s1 is equal to 24. The only value that s1 can take on is 24. In the next row, all right, I gotta know, no one's looking at me and everybody seems to be working, so what am I going to put in this box? Answer in the chat, please. Okay, so it looks like those of you that are answering quickly see what's going on. Thank you. 3. What about here? All right, so x2 is 0, s1 is 0. 3 times what is 24? So some of these systems are, much easier to solve than others, but all of these are feasible because for every one we've got a non-negative value for s1. So the second part of this is for each basic solution indicate whether or not it's feasible. So all 3 of these solutions are feasible. And, I guess technically if you want to write them down, you've got to write them as an ordered triple. And so 0, 0, 24, 0, 3, 0, and 8, 0, 0. Okay, I think we have time for one more. Let me give a number 62. We have the objective function that we're going to bring all the terms over to the left and make it equal to 0. We've got a couple of slack variables here because we have 2 constraints, and we have x1 greater than or equal to 0, x2 greater than or equal to 0. So in our table, we have x1, x2, s1, s2, and then the value of p, which is 5x1 plus 20x2. All right, now the number of rows you have for this table, you have 2 slack variables, so m is 2. 2 times, if you add 2 to 2, you get 4, 3 to 2, or 1 to 2, you get 3, 4 times 3, 12 divided by 2. You're going to have 6 rows here. And here they are. So you start off with x1 and x2 0, then x1 and s1, then x1 and s2 be 0. 2 of the 4 variables must be equal to 0. All right, and we'll jump to x2 and s1, x2 and s2, and then finally the last 2. And you have to solve a system. So these problems are going to be long because you're going to have to solve a system of equation 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 12 systems of equations you'll have to solve. Some are easier than others. All right, so if these 2 variables, x1 and x2, are both 0, 0, and 0, then we have s1 is equal to 15, and s2 is equal to 7. If x1 and s1 are equal to 0, so the x1 is 0, and the s1 is equal to 0, I'm just going to cover them up, then what we have is x2 is equal to 15, and if x2 is equal to 15, then S2 has to be -8. So X2 is 15, and that makes S2 equal to -8, and this one is not feasible. So I won't even go calculate the value of P there. In the next one, S2 is 0, and so is X1. So I'm going to just get rid of the X1 variable because it's attached to 0, and then X2 is also 0. S2 is equal to 0. So you can see from what remains from the second equation that X2 must be 7. And if X2 is 7, and you put a 7 there for X2, then S1 has to be 8. So this one is feasible. All right, now I'm going to wipe out the X2s and the S1. So 5X1 is 50. Oops, you can't see that. 5X1 is 15. So X1 must be 3. And then 3 plus what is 7? 4. That one is also feasible. All right, in the next row, okay. I'll complete this one. We're out of time. I'll complete this one outside of class so you can see how the rest of this would work. And this would be, again, the rest of this is to fill in these two numbers, calculate all the P's, and identify the ones that are feasible and those that are not feasible. And if they're not feasible, then you don't even need to evaluate P, but for all those that are feasible, go and just compare them. And the one that's the largest is what we're going to call the max. So I'll finish this one up and include it in the notes.